Rigging's a very specialized skill, one that requires both experience and study. You've already learned the basics. You've learned to plan a rigging job, how to inspect rigging equipment before a job, and how to move a load safely and efficiently. By now, you've had a chance to do some rigging work, and you've found out that some jobs are more complicated than others. To be ready to tackle any rigging job, you have to develop your skills and learn more about the specialized equipment used for lifting and moving loads. We'll be talking about periodic equipment inspections and the kinds of records that have to be kept. We'll see some of the special techniques used for really big loads and others for performing complex maneuvers with chain hoists. Other skills you'll learn include figuring sling tension and capacities, crane operation, and working from different kinds of scaffolding. Every rigging job's different in its own way, but the same kinds of skills are used in all of them. Likewise, the same kinds of safety precautions are required on any rigging job. When you're talking about moving several tons through the air, your own safety's got to be the most important thing of all. Basically, rigging safety's common sense. That and following a few rules born from past experience. Usually, they're lessons learned from other people's mistakes. Perhaps the most basic rule of all is, pay attention to the job. Every rigging job can't be interesting, but they all have the potential to become exciting very quickly. Horseplay's out for the same reason. Frightening someone might make them do the wrong thing, and something valuable might be damaged. Something valuable, like your own head, for example. One of the most important rules of all is to keep people out from under the load. No one should walk beneath a suspended load. The same thing goes for any part of your body. Hands and feet don't have any business underneath a load. Riggers don't have any business on top of a load either, not when it's up in the air. Riding a load or riding on the load hook of a crane is not a good way to save time. If you have to work aloft, there's special equipment you can use. On any rigging job, one person has to be in charge, and only one person should be giving signals. A crane operator has enough to do without having to figure out which signal is the right one. Throughout this session, we'll be watching riggers perform a variety of different jobs, and you'll notice that they all wear protective equipment. Hard hat and gloves, those are the bare minimum. It's easy to see why. A hard hat protects your head from falling objects and bumps when working in tight places. It'll lessen the force of a blow from any source. Heavy gloves are important in rigging work because you often have to handle wire rope, chains, and other equipment that can cut, scrape, or pinch your hands. In addition to a hard hat and gloves, some jobs require eye protection as well. In rigging work, you're often looking up where the load is. And when you've got moving lines and sheaves, it's not uncommon for little particles to fall down on top of you. If you're looking up when they fall, they go right into your eyes, unless they're protected. Here's another item that's good to use. Safety shoes with steel toes to protect your feet from crushing. When you're working overhead, lifelines are a good idea too. They can save your life if you slip and fall. But protective equipment isn't all there is to safety. Good practices are just as important. Handling hooks and tensioning slings has to be done right to be safe. The main thing is to keep your hands and fingers away from pinch points. It's really a matter of paying attention to what you're doing and where your fingers are. Lifting and moving the load is the most critical part of any rigging job. The right way to do it is slow and easy. Rushing a job can be an occasion that might require a person to be rushed somewhere else, like to a hospital. These are really the basic points. Just the first of many things you have to know to be a safe rigger. Rigging can definitely be just as safe as any other line of work, But it takes concentration and skill to keep it that way. Safety has to be a big part of any rigging job. As you acquire more experience in rigging, you'll learn more of the skills you'll need to know for safety's sake. And as you develop these skills, you'll be learning to be a more efficient rigger as well. In a few minutes, we'll be back to start on the advanced techniques that distinguish an experienced rigger from a beginner. But before we go, take some time to look through section 1 of your text and work the exercises. When you're lifting and moving heavy loads, the dependability of your equipment really counts. Rigging equipment sometimes takes quite a beating, and it's especially important to your safety that it stays in good shape all the time. Now, your basic training in rigging included some inspection procedures. We talked about the kind of inspection that's part of preparing for any rigging job, but the checks you do before you put the equipment on the job are only half the story. What we're going to talk about now is periodic inspection of rigging equipment. These checks are made at regular intervals of a month or a year or somewhere in between, depending on the type of equipment. There are two main differences between periodic inspections and the kind you do immediately before a job. First, periodic inspections are much more thorough. In many cases, they involve disassembling the equipment, checking all its parts, and reassembling it. The second difference is that written records are used to keep a running report of the equipment's condition. These written records are important because they allow you to document any damage, and that way you'll be able to catch equipment failures before they happen. We're going to see how several different kinds of rigging equipment are inspected. In each case, you'll notice that a checklist is used to record the condition of the item. These checklists are kept on file. When new equipment's brought in, its original condition is noted. Every inspection that follows is filed with the original report so that common types of damage can be identified and average equipment lifetimes can be figured. This not only helps determine a maintenance and a replacement schedule, but it also points out the kinds of wear and damage that are most common for each type of equipment. Each report is signed and filed by the person who's responsible for the inspection. We're going to see the inspection procedure for three basic kinds of equipment: slings, jacks, and hoists. In each category, there are several special cases to consider. We'll start with slings. Here in the tool room, there are several kinds of equipment due for periodic inspection. For starters, we've got some chain slings that have to be inspected. The checklist shows each of the points that have to be checked. First, a visual inspection is made of each link to check for cracks and make sure each of the links hinges freely with the adjacent ones. Any cracks or frozen links would be enough to retire this chain from service. Each end attachment is checked for cracks, bending, and wear. The chain itself is checked for wear by measuring the diameter of the stock. A micrometer or a set of calipers is used to make an accurate measurement. The diameter is noted on the checklist to become part of the permanent record of the sling's condition. Then a table is consulted to see whether the amount of wear is excessive or not. The table lists the maximum allowable wear for chains of every size. For a 3/8 inch chain, the limit is 5/64. As long as the chain hasn't been worn down that far, it's still okay to use. If some of the links are nicked, the nicks can be ground out, as long as you don't have to grind any deeper than 5/64. The next thing to check for is stretch. You can check for stretch by measuring the length of a 5-link section with a ruler. This measurement is noted along with the others on the inspection record. Any chain will normally show some stretch when it's been used regularly. To check for excessive stretch, you have to consult the manufacturer's specifications to see how much is allowable. As long as the chain's within those limits, it's safe to use. When the inspection's complete, the report's signed by the inspector. The report's then placed with the sling's previous inspection records. Since it had no major problems, it'll be filed away so it'll be available whenever someone has to check it. Roller chain has to be inspected for several different kinds of damage. The first thing to check is camber, the amount of side bow in the chain. The easiest way is to use a straight edge. You can sight along the straight edge and see just how much of the chain bends to the side. When the chain is laid out as straight as possible, the chain shouldn't be bowed out more than 1/4 of an inch in a 5-foot section, or 8 millimeters in a 2-meter length. The next thing to look for is twisting. In a 5-foot section of chain, that's about 1 2/3 meters, there should be no more than 15 degrees of twist. To check for stretch, measure out a 1-foot section, that's about 1/3 of a meter, and count the number of links, including fractions. Checking the specs will show you just how much the chain is stretched. If it's stretched out more than 1/4 of an inch in a 1-foot section, or 2 centimeters in a 1-meter section, it's no longer safe. Finally, the entire chain's given a thorough visual examination. Each roller should rotate easily, and the joints should all flex without too much pressure. Check for any corrosion or rust, and make sure the pins are tight. This chain's lubricated with motor oil. Others may require different lubricants. Be sure to check the manufacturer's specifications before lubricating any roller chain. Back in the tool room, sling inspections continue. This time, it's wire rope slings. The first thing's a visual inspection. Broken wires, wear, kinking, or crushing are all possible defects that could cause the sling to be rejected. Eye splices should be inspected to make sure they're tight and secure. As a final check for wear, the diameter of the rope is measured with a micrometer or calipers and compared with the original specs. It should be within 10%. This sling is relatively new. No significant wear is apparent. This sling, however, is a different story. It's been through some hard service, and it shows. This shiny patch shows that the sling's been severely worn. As you can see, it's worn right down through the outer wires. This sling's no longer safe and will have to be destroyed. Damaged slings are always destroyed, not just thrown away. That way you can be sure they'll never be used by mistake. Cutting the sling into short sections is the best way to do the job. Pieces this size can't be used again. Just like roller chains, wire ropes have to be lubricated at regular intervals. This eases the friction of the strands moving past each other. A spray lubricant's being used on this rope. The manufacturer's recommendation should be followed precisely, using only the specified lubricant. The last type of sling we'll see is made of synthetic webbing. The first thing to do is carefully check its entire length for cuts, wear, and heat damage. The stitching should be inspected closely for any unraveling or broken threads that might cause the sling to come apart. This sling's designed with red fibers embedded in the material. That way, when it starts to wear thin, the red fibers will show up on the surface. Since this sling's made with metal end attachments, they have to be checked for cracking and bending that might indicate that the sling's been overloaded. Just as before, The inspection report is filled out completely to record all of the worn and damaged places on the sling, whether it needs replacement or not. Here's another item that needs to be inspected: a fiber rope. Synthetic ropes and manila ropes, like this one, are often used for lifelines or taglines, and they have to be inspected just as carefully as slings do. Twisting the strands apart makes it easy to check for broken fibers, burns, and worn places. Any powdered fibers between strands are a sure sign of wear. The rope appears to be all right, but the ends are badly frayed. That'll be fixed right away. To keep the rope from fraying more, it'll have to be whipped. Whipping the end of a rope is a technique of binding it up with something like fishing line. Starting with a short length of line, cross the two ends about ½ an inch back from the end of the rope. Then wind the loop around the rope so that both of its ends will stick out beneath the windings. When it's all wound on, the whipping's tightened by pulling on the two ends. When the ends are trimmed, the rope has a neat, tight winding that won't unravel on the job. So far, we've seen how slings and ropes are inspected and cared for. Now we'll see two more kinds of equipment undergo their periodic inspections: jacks and hoists. This is a screw jack. The first thing to check for is any loose bolts or rivets on the housing. The housing itself should be checked for cracks. Next, check the action of the ratchet and pawl. Pumping in this direction should raise the ram smoothly. Moving the pawl to the other position should change the direction of motion. Now the jack should lower easily, without slipping. To check the ram, pump the handle until the ram's fully extended. Then check the sides for scoring or other signs of damage. The cap on top of the ram should also be in good condition, flat, not bent or dented. If everything checks out okay, the inspection report's filed as usual. If any significant damage is found, though, the jack may have to be disassembled to check the condition of its internal parts. Hoists have to be disassembled yearly to check the condition of their operating parts. But before they're taken apart, their chains and hooks can be inspected. Lift chains are inspected for the same kinds of things as chain slings are. The chain's given a thorough visual inspection for cracks. Its size is measured and compared with the original specs. And the length of a 5-link section is measured to check for stretch. Next, the anchor pins checked to make sure the lift chain is firmly attached to the hoist casing. Once the chain's been inspected, the next thing to inspect is the hook and its connection to the lift chain. The hook itself is usually checked with a non-destructive testing method called dye penetrant testing. The penetrating solution sinks into any cracks and reveals their location when a developer is added. While waiting for the dye to penetrate, the hoist can be taken apart so that its internal parts can be inspected. All the gears, sprockets, brake pads, and ratchets can be examined firsthand. After it's been reassembled, the hoist will be tested under load to make sure everything works properly. These are just a few of the inspections that have to be performed on rigging equipment on a regular basis. Every piece of rigging equipment has to be checked, and all the important points made part of a permanent record. These permanent records are one difference between a periodic inspection and the type of checks you have to do each time the equipment is used. The other difference is that a periodic inspection is much more thorough. Since all equipment varies somewhat according to the manufacturer and the particular model in question, the manufacturer's recommendations should always be checked before a periodic inspection. This information lists the original specifications for the equipment and any additional points that should be inspected at regular intervals. Lubrication and repair should always follow those guidelines. That way, you know the equipment's being maintained just as the manufacturer intended. In a little while, we'll be back to see how some of these kinds of equipment are used for several different kinds of rigging jobs. Meanwhile, read your text for additional detail on these inspection procedures. When we return, we'll see some ways to lift and move extremely heavy loads without hoists or cranes. There are lots of ways to move heavy loads. You've already seen some of the ways hoists and cranes are used for various jobs. We're going to talk about some advanced techniques now. These are ways of lifting and moving loads without hoists or cranes. Jacks and rollers can be used when other devices aren't available in the capacities necessary for an extremely heavy object. In many ways, these are very old techniques, but modern jacks make these jobs both easier and safer than in the past. We'll be watching a few different jobs using jacks and rollers. In each case, we'll see the techniques involved and we'll see the special safety precautions you have to use when you're doing these jobs. To begin, let's take a look at a typical job done with mechanical jacks. Here we're raising a load up to the level of a loading dock. We'll use 4 jacks to lift this transformer. The first thing you notice is that each jack sits on a wooden 4x4. This serves 2 purposes. First, it keeps the base of the jack from sinking into the ground under the weight of the load. Second, it keeps the base of the jack level, so it won't tip over and accidentally drop the load. This is called blocking the jack. Here, on top of the jack, is another piece of wood. 2x4s are used between the ram and the load's lifting lugs to eliminate any metal-to-metal contact, which might cause the jack to slip off the load. Since the ground surface here is not entirely level, each jack is set to a different height. All 4 have to be raised simultaneously and evenly so that the load remains level, supported equally by each jack. A bubble level can be used to make sure the load's level. Keeping the load level prevents rocking or tilting. Each jack must be vertical to keep it from kicking out under the weight of the load. As the load's raised, timbers are placed underneath. Riggers call this technique cribbing the load. Cribbing serves 2 purposes. First, if the load slips off the jacks, it won't fall far. Also, the cribbing supports the weight of the load while the jacks are reset. Each time the jacks reach the limit of their upward movement, another level of cribbing is added. Then the load is jacked down so that it's supported by the cribbing. To raise the load higher, the jacks have to be reset. The rams are lowered and more blockings added beneath each jack. This additional blocking sets the jacks higher so the load can be raised again, high enough for another level of cribbing to be added below. Cribbing is positioned in a crisscross pattern like this. As each level is added, 2 timbers are laid at right angles across the cribbing below. As additional levels are built up, each timber forms part of a solid square structure for the load to sit on. By alternately adding cribbing and resetting the jacks with extra blocking underneath, a load can be raised in steps as high as necessary. Whenever you're jacking a load, you're dealing with a potentially tricky situation. A heavy load's being supported at several individual points, so balance is crucial. The load has to be level, and the jacks have to be vertical. Otherwise, you're asking for trouble. It's no joke when you've got a couple of tons tipping over on top of you. To keep the load level as it's being raised, it's important that all the jacks are the same type. They all have to be raised together. And if they're going to keep the load level, one pump of the handles has to raise each jack an equal amount. Otherwise, one jack may be coming up faster than the others. Usually, the lead man on the job calls out the rhythm, so everybody's pumping together. Besides having jacks of the same type, it's important that every jack be in good mechanical condition and have the necessary capacity for its part of the load. For example, if you've got 4 jacks and a 20-ton load, the jacks have to be rated for at least 5 tons apiece. Often, jacks are built so that it's impossible to raise a load heavier than their capacity. Hydraulic jacks sometimes have a pressure release device. When the jack's overloaded, it'll just stop. You could pump all day and the ram just wouldn't go anywhere. Other kinds of jacks are often made with handles of a certain length so that a person of average strength will have just enough leverage to lift the rated load. If it's too hard for one person to do, the jack's either overloaded or it's in poor mechanical condition. Adding an extension on the handle, a cheater bar, can be dangerous when this is the case. The jack's not big enough for the job, and failure under load can have some pretty bad consequences. With all this in mind, let's look at another typical job using jacks. This time we'll see step jacks being used. They have a ratchet that raises a rack 1 step for each time the handle's pumped up and down. These step jacks are being used to raise a pump rotor high enough to be placed on stands. Notice that the workers are pumping together. They've got the rhythm down so the load's raised evenly and stays level all the time. These jacks have been permanently mounted on wooden bases. The bases keep the jacks vertical and help prevent them from kicking out under the load. As the workers jack the load, they're careful not to lean over the jack handles or straddle them unless both hands are on the handles. With a mechanical jack, it's possible for the ratchets to slip, making the handle kick upwards, and they could kick back with a lot of force, and this can be a very painful way of learning the high jump. As the load reaches a height slightly above the level of the stands, the workers stop jacking and position the stands under the shaft. They're carefully placed so that the load can be lowered down on them squarely. To lower the load, a pawl on each jack is switched to reverse the direction of the ratchet. Then, pumping the handles lowers the load instead of raising it. When the load's securely supported on the stands, the jacks can be removed. Up to now, we've seen how to raise loads with jacks when you don't have a crane to do the job. Well, there are also situations where you have to travel a load without a crane. One technique you can use is moving the load on rollers. This is one of the oldest rigging techniques still used today. It's said that the ancient Egyptians moved the stones for the pyramids with this technique, and some of those stones weighed as much as 30 tons apiece. In those days, construction projects had to rely on muscle power alone for all the heavy jobs. It's a little easier today. We're going to see a load pulled along rollers with a winch. This speed reducer weighs about 3 tons. It's mounted on a skid to give it a broad, smooth, lower surface. The skid's rolling on 4 pieces of pipe. As the winch pulls the load along in short steps, the rollers in back are picked up and placed ahead of the load for the next short pull. The operation can be repeated as many times as necessary. Boards are laid out under the pipes to give them a smooth surface to roll on. Rollers can be used to make a load turn corners too. To do this, the pipes are turned at angles. The rollers can be turned by inserting bars in each end of the pipe and pulling in opposite directions. This is called cutting the rollers. To make the load turn smoothly, we cut the rollers so they're fanned out. They're closer together on the inside of the turn and far apart on the outside. Since the rollers rotate beneath the load, you have to be careful not to use too many rollers on a turn, otherwise they might bunch up and make it harder to pull the load along. Rollers are a good way to move extremely heavy loads from place to place, but you've got to be extremely careful of your hands and feet. It's no fun to be run over by a load that's supposed to be under your control. To make rolling a load safe, placement of the rollers has to be well coordinated with the winch operator. Rollers shouldn't be moved until the loads come to a complete stop. Using rollers to move a load is an advanced technique that requires only the simplest tools. When jacks and rollers are used together, you can take a load just about anywhere. In the past, jacking and rolling were the only ways to move heavy loads from place to place. Today we have hoists and cranes that perform many of these jobs. As a result, jacking and rolling are used primarily where cranes and hoists aren't available, or when loads are too heavy for existing equipment to lift. In a few minutes, we'll see some special techniques that are used for manipulating loads with chain hoists. Until then, study the section on jacks and rollers in your text. Knowing all the techniques available to you is a big part of being a complete rigger. And a complete rigger can move anything, anywhere. If you've done any rigging at all, your previous experience probably includes using a chain hoist. Hoists like this one are pretty adaptable tools. You've seen how they can make straight lifts when they're suspended from the overhead, and you may have experience using one or more chain hoists on the load hook of a crane for leveling or fine control of a load when it's being raised and lowered. What we're going to do now is talk about 3 specialized operations you can do with hoists: tilting a load up on one end, turning a load over, and walking a load. Upending a load can be done with one hoist. Turning a load over is done with 2 hoists. Walking a load is when you use 2 or more hoists to travel a load when you don't have a crane or rollers. We'll start with turning a load on its end. We want to rotate this load to the right so that it's standing on what's now its right side. Before we rotate the load, we have to find 2 things: the load's center of gravity and its tip point. This load is a regular shape, and its center of gravity is right about in the middle. The tip point is here. This corner will act as a pivot as the load's tilted up on its side. These 2 pieces of information help us decide where to attach to the load. Imagine a line that extends from the tip point through the center of gravity and beyond. On this load, it crosses the corner opposite the tip point. The best place to attach to the load will be right below this line. When we lift from this position, the load's controlled all the way up. As the center of gravity passes the tip point, the hoist can be used to set the load down gently. You'll notice that we need some travel on the hoist to make the motion smooth. Let's see what happens when we attach at a different spot. This time we'll attach above the line. The load rises easily as before, but when it's tilted as far as it'll go, the center of gravity doesn't pass the tip point. Instead, the load's lifted off the floor. To make the load tip up, we'd have to push the load over. It's not really under control. Here's what happens when the lift point's too low. Once the center of gravity passes the tip point, it tips over suddenly without positive control. This can easily damage a load. For our last example, let's see what happens when we tilt the load up without hoist travel. As it's tilted, the bottom corner drags across the floor. Unless a load is specially protected, you don't want to tilt it this way. Most of the precautions involved with this procedure are aimed at preventing damage to the load. There are really 2 key points to remember. First, you have to select the right lift point, and second, the hoist has to travel. This can be done either with a crane or a hoist on an overhead track. The next operation we're going to see is turning a load over, so the bottom side will be on the top. We're going to be using 2 hoists to turn over this pulverizer rocker. The first step is to attach a sling to one end of the load. The sling's coupled to hoist number 1. As the slack's taken up, one rigger tensions the sling so it doesn't slip out of position. When the sling's tight, he changes position so he can steady the load as it's lifted off the floor. Since the lift point's off-center, the load will tend to swing unless it's held onto. This hoist doesn't travel, so there's no way to avoid having it slide on the floor to some extent. More Fragile components would need special protection underneath. The load's raised until it's slightly off the floor. Then another sling is attached to the other side of the load. This time they're using an endless sling to make a basket hitch. Both end loops of the sling are attached to the load hook of hoist number 2. As the second hoist is raised, it slowly rotates the load, pulling it around so that its weight is evenly distributed between the two hoists. The load steadily cranked around until it's past the perpendicular position. Then padding's placed between the sling and the component to keep the sling from damaging the flange. Once it's past this point, the first hoist is lowered so that the load begins to level out. When it nears the floor, both hoists are lowered away. Then the load's gently landed on the floor, upside down from its original position. These are two ways of handling a load and putting it in just the position we want: turning it on end and turning it all the way over. Both of these operations can be performed either with hoists or with cranes. Next, we're going to see a method for moving a load to another place without a crane, skids, or rollers. It's called walking a load. The first thing is to get the load up in the air. Here we're using one hoist with a come-along to balance the load. When the load's off the floor, the second hoist is attached to the same shackle. Then the first hoist is cranked up so that the load will be a little higher off the floor. The second hoist is raised to take up the slack in the load chain. Now both hoists are supporting the load's weight. As the second hoist pulls the load to the side, the first is let out to keep the load at about the same height. The load's not lifted any higher than is necessary for the job. This is what walking a load really means: moving it from hoist to hoist in short steps. When the first hoist goes slack, the load will be directly beneath the second hoist. Then the first hoist can be moved beyond the second one, and the operation can be repeated, one step at a time. As the load moves toward the right, the second hoist bears more and more of the weight. When the first hoist's load chain begins to slacken, its hook will be removed from the load. While the second hoist holds the weight, the first hoist will be moved to another position to the right of the second hoist, and the process will continue. What you've just seen is the simplest way of walking a load. Only two hoists are required, and a load can be traveled any distance, as long as there's something overhead from which hoists can be hung. We're going to take a look at another method now. It's a three-hoist technique. It's used when you have a long or bulky load, and you have to use two hoists just to get off the ground under control. Here's the load suspended from two hoists. The next step is to add a third hoist, attached to the overhead along the direction of travel. As you tighten up on hoist number 3, the load moves to the right. Once it's in this position, it's being supported evenly by hoists number 1 and 3. So hoist number 2 can be switched to the trailing end of the load. Hoist number 1 can then be slacked off until the load is suspended directly beneath 2 and 3. Then number 1 can be moved, and the process repeated. Walking a load's a special technique that's used in a variety of situations, whenever you don't have a traveling crane, a dolly, or rollers to do the job. Whether you're using two hoists or, for some larger loads, 3 or more hoists, the principle's the same. You walk the load along by progressively moving your hoists farther along the direction of travel. As you take up on the hoist in front, Slack off on the rear hoist to keep the load level and at about the same height. So far, we've discussed 3 special hoisting techniques: turning a load up on end with one hoist, turning a load over using 2 hoists, and walking a load with 2 hoists or more. These are just a few of the ways that you can use chain hoists to handle a load that's too heavy to move by hand. Later, you'll get a chance to try out these techniques as practice exercises. When you do, remember 2 safety points. First, don't load a hoist at too much of an angle. Try and keep the lift chains as close to vertical as possible, since angled lifts increase chain tension. Second, make sure you've got a solid connection to the load. Pad eyes or shoulder-type eye bolts are necessary whenever you're pulling at an angle. Before we go to our next topic, take this chance to read section 4 of your text and work the exercises. There'll be some additional detail there, and if you have any questions, ask your instructor. You already know quite a bit about slings. We've seen how they're inspected and talked about some of the ways they're used. In general, slings are used to attach a load to a hoist or another lifting device. All slings, whether they're made of wire rope, chain, or synthetic fiber, have a rated capacity that indicates the maximum safe load for the sling. What we're going to do now is talk about how a sling gets rated to begin with and how its capacity is affected by the way it's rigged. Although the same factors apply to all types of slings, we'll use wire rope in our examples. First, we'll talk about rated capacity. Now, 2 factors come into play here: the breaking strength of the rope and the efficiency of spliced or end attachments. The breaking strength of a rope is tested at the factory by taking a sample of the rope and pulling it with special machines until it breaks. The amount of pull, measured in pounds or kilograms, is the breaking strength of the rope. When figuring the rated capacity of a wire rope, we take the breaking strength and divide it by a safety factor. Usually, for wire rope slings, a safety factor of 5 is used. That means that the rope will have to be subjected to 5 times its rated capacity before it breaks. This extra margin of safety can really come in handy, because shock loading or invisible damage can greatly reduce the breaking strength of a sling. The second factor we mentioned was the efficiency of the splices or end attachments used on the sling. Most wire rope slings have eyes at either end. The eyes can be formed in several ways. They can have a hand-tuck splice, a mechanical splice, or they can have a poured zinc socket. Now, hand-tucked splices are the weakest. They'll fail at some point between 70 and 95% of the breaking strength of the rope. So they're said to have a 70 to 95% efficiency. Mechanical splices or poured zinc sockets, properly applied, are much stronger. Many are said to be as strong as the rope itself, or 100% efficiency. These mechanical splices and poured zinc sockets don't weaken a sling at all. Okay, those are the factors that affect the rated capacity of a sling, but that's only half the story. In any given application, the lifting capacity of a sling hitch will also depend on how the sling is rigged. The actual tension on a sling is what's important. It's affected by 4 different factors. 1, the number of sling legs used in the hitch. 2, the type of hitch. 3, the diameter around which the sling is wrapped. And 4, the angles of the sling legs. The first factor that affects sling tension is the number of sling legs that attach to the load. Now, some slings are made up in 2, 3, or even 4 parts. If 2 vertical legs are used, each sling must support only half the weight of the load, so each leg has only half the tension that a single sling would have on the same load. In effect, this doubles the rated capacity. Be careful, though, that you don't make this mistake. When a single sling is used for a 2-leg bridle, it still only has the strength of a single sling, even though there are two sling legs. All the tension is concentrated here, where the sling passes over the load hook. This hitch isn't recommended for two reasons. First, the rope may develop a kink at the hook, and second, the sling may shift position on the hook, throwing the load off balance. The second factor in sling loading is the type of hitch used on the load. For example, a choker hitch concentrates the tension here, where the choker cinches. The tension here will be 1 1/3 times greater than if a single vertical sling were used. So a single choker sling has to have a rated capacity 1 1/3 times greater than the weight of a load. Basket hitches work in just the opposite way. Tension is distributed evenly between the two legs. As long as the legs are vertical and the sling isn't bent too tightly at the bottom, each leg has to support only half the weight of the load. This brings us to our third factor, the diameter around which the sling is wrapped. Tension is concentrated where slings have to turn sharp corners. The tighter the bend, the more tension is produced. The fourth and last factor that influences sling capacity is sling angle. When bridles, double chokers, and double baskets are used, they're strongest when the legs are vertical. The wider the legs are spread, the more tension is produced. The same thing goes for hoists when 2 or more of them are used to hitch a load. This demonstration should help show you what I mean. Here's the hoist, and here's the load. This load weighs 2 pounds. We'll be lifting it with 2 slings. Attached to each sling is a spring scale, just like one you'd use to weigh a fish. We'll use these 2 scales to measure the amount of tension on each sling leg as we vary the angle. The protractor at the load hook will show the angle we're using for each lift. We'll start out with both slings straight up and down, 0 degrees from vertical. The scales show that each sling has 1 pound of tension. Each one is supporting half the weight of the load. Next, we'll move our slings out to a 30-degree angle from vertical. Let's see what the scales read when we hoist the load now. Each scale reads 1 1/4 pounds. Each sling is under 1 1/4 pounds of tension. If we add the 2 measurements together, we get 2 1/2 pounds. So the total amount of tension on both sling legs is greater than the weight of the load. That's because the slings are spread out at an angle. They're being pulled outward and downward. As we increase the sling angle, the tension should increase. Let's see what happens. Okay, now the slings are set at an angle of 45 degrees from vertical. When we hoist the load and read the scales, we get 1 1/2 pounds of tension on each sling. That's a 1/4 pound more, or 20% more, than our measurement at 30 degrees. Let's try a couple more measurements and see what we get. Now each sling is adjusted so that it's 60 degrees from vertical. When we raise the load and read the scales, we can see that the tension of each leg is 2 pounds, the same as the weight of the load. The total tension on both legs is double the weight of the load. That means if you're lifting a load with a 2-leg bridle hitch and each leg is set at 60 degrees from vertical, each sling leg must be able to support the entire weight of the load, even though there are 2 slings to share the weight. Let's see what happens if the slings are rigged at an even more extreme angle. Now we've shortened both slings, so their angle from vertical is 80 degrees. Now we'll raise the hoist, and each scale shows a tension of 6 1/2 pounds. The tension on each leg is over 3 times the weight of the load. Because of this sling tension effect, slings should never be rigged at an angle more than 60 degrees from vertical. Any more than that, and each sling has to withstand a tension greater than the weight of the load. Sometimes, though, you might have to rig a load with an especially wide sling angle, like this one, because of limited headroom or for some other reason. If you do, be sure to select slings with a capacity more than 3 times the weight of the load. That way, they won't be overstrained when the load's picked up. So far, we've talked about how slings are rated for a certain capacity and how that capacity is affected by the number of sling legs, the type of hitch, the diameter around which a choker or basket is wrapped, and the angle of the slings. Each of these factors affects sling tension, and we've seen that sling tension is often only indirectly related to the weight of a load. So on the job, you're going to need a quick and easy way to figure the tension on your slings. Well, the best way is to use a rigging table. Your textbook contains tables like this one in the appendix, with instructions on how to use them. There's a different table for each type of sling construction. By knowing the weight of the load, you can figure just what size sling you need for any kind of hitch or sling angle. If you have to figure sling tension more accurately, there are some easy calculations that allow you to figure just how sling angle affects tension. These calculations, with instructions, are also in your text. Learning how to use rigging tables and do simple calculations is one part of becoming an experienced rigger. The other part is practice. So far, we've discussed rigging safety. We've seen how equipment is inspected. We've learned some of the ways rigging equipment can be used to move heavy objects without cranes. As you practice these skills, build upon what you've learned here. Rigging isn't hard. It's all in knowing how to do the job safely.